Take your seats. Okay, so it's 10 minutes past 4 o'clock, so we start. General comments. You saw that I put on the website the file for this lecture. I will put the rest of the lectures hopefully this week or next week, because we agreed on the order of the lectures. Today I will talk about lithography. It's a very heavy topic. Sometimes I give a full semester only on lithography, which is 13 lectures on lithography. This semester I'm giving one lecture on lithography, so this is just an overview about lithography. And I will focus on high-resolution lithography and what we call nano-lithography with critical dimensions in the nanometer range. If you want to learn more, you are invited to read this book, the book by Chris Mack. You have the online course, which is a very nice one. The book Micro Lithography, Science and Technology, and the book by Harry Levinson, Principles of Lithography. It's a very good book. There are not many books which are covering all lithography, so to my opinion, this is the best book, especially for optical lithography. And today, companies print using optical lithography circuits with critical dimension, and I will explain to you what does it mean, critical dimension, but you can imagine that they can print a feature with a dimension in the range of 7, 8 nanometers using optics. And in this lecture, I will explain to you how you can take an imaging system with a wavelength in the ultraviolet, which is 193 nanometer, and print a feature which is a 6 to 7 or 10 nanometers, which is much, much shorter than the wavelength. So I'm going to talk about basic optics, and I'm going to talk about what we call the photolithography process. And practically, the process in this lecture, or what we call photolithography, is based on 3 steps. There are 3 steps. First, we put a light-sensitive material. We call it Photoresist. And you can understand why we call it Photoresist. It's a photo responsive material. It's a material which responds to light. And you can remove it or keep it, depends on the illumination. You coat the whole surface by the photoresist, by light-sensitive polymer, and you illuminate it, and by illumination you induce some chemical reaction or photochemical reaction. So you coat the photoresist, you expose it. This is a typical exposure system. You have a mask, you illuminate it, light is penetrating through the mask. The mask itself has features which are very, very small. So the light, which is the electromagnetic wave, when it goes through the mask, it's not just like particle going through a mask. You have diffraction, you have interference, you have other phenomena which you have to analyze. So the light is going through the mask, being diffracted, is collected by the lens, and you got here the image. And typically, the image is much smaller than the mask. I say typically because there are systems where the image is of the same order. But in principle, in many of these exposure machines, the image is much smaller than the mask. This is a very important fact. And this concept was introduced to the industry in the 80s, when approximately when I was a student, so you can imagine my age. And this was a breakthrough. Because until then, people take the semiconductor, put the mask on the semiconductor, and take the image. It works fine. Actually, you can get very good resolution. The problem, every piece of dirt that you have on the mask you print it on the wafer. So if you take a mask and you reduce the image, what happened? The mask is here, the wafer is here, the mask does not touch the wafer. In our lab, in the student lab, we have a machine, it's called contact printer, and you can imagine what does it mean. You take the mask, you put it on the wafer, and you can print your device. But a PhD student needs only one working device to get his PhD. So if you have like 100 or 1,000 devices and 2 of them are working, he's happy. But if you're a company, you are absolutely unhappy. You want all the chips to work, and you cannot tolerate even single defect. So the concept of projection imaging is the dominant project today in the industry. Luckily, you can also get unbelievable, incredible resolution using this method. So it's not only saving your mask and protecting your wafer, but you can get very good lithography. So and the last step is called development. After you expose the photoresist, you remove everything. You expose the pattern out of the latent image. And I will explain to you during this lecture what does it mean, a latent image. A latent image is after exposure of the resist, you illuminate it. So you do some chemical reaction, which means there is something inside the photoresist which you need to develop and expose and remove whatever you don't need it. This is, by the way, it's called negative lithography, which means you coat and you remove what you don't want to use. There is another concept called additive printing. For example, you have it at home. It's called inkjet. You put a paper and you print only in the places that you need. So inkjet is positive printing, or laser jet is a positive printing. It's a wonderful concept, but it's not high-resolution concept. You cannot print 7 nanometer feature with an inkjet at high speed. So for high-throughput lithography, when you need to print electronic circuits and you need to print many, many features, you use this concept of projection lithography. And just to demonstrate to you what you have the wafer, you have the mask, this is your light source. If the mask is in contact with the wafer, we call it contact printing. And I will not talk today about contact printing. It's a very trivial process. What's relevant is the behavior of the photoresist. Practically, you generate a shadow, and the shadow, nothing happens, and the illuminated part, you have the photochemical reaction. You can also keep it with some spacing. This is called proximity printing. This is very common for very large area printing, for PC boards, for example. Also in cases when you don't care much about resolution. Because as you know, if you take the mask and if you look at your shadow, if you move away from your shadow, the boundaries of the shadow becomes fuzzy. So if you take the mask and separate it from your wafer, the image is not so much high quality. But in some applications, it's okay, especially for large area PC board, which is a large area device, and you need a cheap device. And what I'm going to talk today is projection imaging, when you take your mask and you take the image of the mask. So you're reducing also the defect on the mask. There's another advantage for projection imaging. If you have masks, if you have defects on the mask, you reduce the defects also. So the defects become smaller, which means also the chance that your circuit will work become higher. Because sometimes the particles or the defects on the mask are so small that you don't even print them because they are below resolution. There's a fundamental, this is a class about engineering, we don't talk about money, but a typical projection system costs today in the range of $20 to $50 million, while a contact printer is about $500,000. So this explains why in the university we use contact print and we don't use projection imaging. What if you go to Intel or Tower Semiconductors or other company, they use projection because This is a very high throughput machine, and also with a very good quality. The concept is, since we talk about engineering applications, since you take your mask and you reduce it, you actually, what you do, let's say this is your circuit. This circuit has some lines and features, some transistors, some resistors that you want to print. You take your mask, the mask is big, 5 by 5 inches, 6 by 6 inches, or if you translate it to centimeters, like 15 by 15 centimeter, and you reduce it by factor of 5 or by factor of 4 or by some factor. So if this is your wafer, and the wafers today are 12 inch in diameter, 30 centimeters. So you print one chip, then you print another chip, and usually the image is fixed and you move the wafer. It's much easier to move the wafer than to move the whole big machine. So this is called step and scan, step and scan, or so you have step between fields and scan, both reticle. There's some other machines that the reticle is moving. Reticle is another name for the mask. You can either keep the mask fixed and the mask fixed and move the wafer, or move the mask. This is called stepper. You have scanner. You can require stage and reticle excellent synchronization. You can also, by the way, you can do focusing while scanning. And printing method, this printing method called step and scan. You can understand that there are possibly various machines. I will not teach you many about machines. I will not teach you a lot about machines. I will focus on the fundamentals of lithography. So the basic requirement, we need the mask. We'll talk about mask. We'll talk about regular mask, but about phase shifting mask, about other features. We talk about illumination systems. People use today lasers, mostly excimer lasers. I'll teach you a little bit about excimer lasers. And most of the lithography today is flat. Most of the applications use very flat surfaces if you want to get very high resolution. And carefully control the environment, vibrations, pressure, humidity, temperature, and light. Of course, if you remember from old lithography days, people use dark rooms. Today, it's not necessarily has to be dark. You can keep the light yellow because the photoresist, the light-sensitive material, is sensitive to blue, to ultraviolet. So the room can be kind of yellowish, in a yellow color. So what is the concept of lithography? It's an image transfer. For example, let's say we have a wafer with silicon, and we have oxide on the silicon. This is just an example. You can think aluminum on glass, or you can think about any material on any material. Just as a demonstration, I'm giving you oxide on silicon, because this is a very common case. And let's say I want to define an area with an oxide on the silicon. So I want a square. I want a capacitor, for example. I want a gate for a transistor. So I have a mask, and on the mask I have a square. Now we have, and you can see here that there are two possibilities. I illuminate it with light, so here there's light around the mask. The mask is masking the light. The mask is an opaque material. The mask can be, for example, metal, can be, in the old days people use silver halide, but the mask is opaque. Here it's opaque. Oops, this is opaque, this is transparent. Here the light goes through the mask, here the light is blocked by the mask. Now we have two possible materials. One materials, when illuminated, they're made of polymers, and when they are being illuminated, they cross-link, which means the polymer become insoluble. And then we dip it, we put it in a solvent, and here it's soluble, here it's not soluble. This is called negative resist. And this is very common in the PC board industry. It's practically a kind of like a rubber-like material when the molecules of the polymer are kind of one into another. And when you illuminate it, you generate a lot of connections between the molecule, and then it becomes very hard and not soluble. So this is called negative resist. It's actually very good quality resist. The problem is on the boundaries. I'll show you later. This type of material, usually the boundaries are not exactly sharp. So you have some limits in resolution. The big advantage is cost and very easy to use. In very high resolution, people usually use another concept called positive resist. This is a resist that usually it's a material which is not soluble. It's a polymer. The most common polymer today is from the Novolac family. It's a brand name. It's a phenolic resin. It's a resin. It's a polymer based on a phenol, which is, by the way, this is very close to what we call formica. It's a very hard photoresist, a very hard material, very hard polymer. But this polymer, you mix it with another chemical, which is called sensitizer, which is has a very interesting property. In this area, where you illuminate it, the polymer becomes soluble. And soluble in a very common liquids, in sodium hydroxide, in a very strong base. So what happens here, we have the polymer, and it's being dissolved all over around it. And I will explain you later why this kind of polymer is very much better resolution or very high resolution. By the way, you can think of it as a kind of a non-linear material. If you illuminate it, it's soluble. If you do not illuminate it, it's not soluble. So this is the concept. Now let's talk about optics. If we look here, this is the block diagram of a generic projection imaging system. You have a light source. It's a lamp. It can be mercury lamp, like people use in high power illumination. And mercury arc lamp, it's a lamp which is based on the light being emitted from mercury atom. It's very, by the way, it's very common for flashes in camera, because you can generate high intensity light at relatively simple lamp. And or alternatively, people use today lasers, excimer lasers which are based on some fluoride or chlorine compounds. Illuminate the light. Usually you have a lens here, because just to take a lamp itself is not good enough. You need to have a lens to make the light coming in an orderly manner. So you design a special lamp, a special light that typically this kind of lamp, sometimes it's called telecentric lamp, which means you illuminate it from the backside and the light is coming out in parallel beam. The light is hitting the mask. The mask has some pattern. The mask is usually made of glass, and the patterns are opaque material. So the light is going through the mask. You generate some interference. Practically, if you learn optics, you are actually generating the Fourier transform of the mask. And the lens is collecting the light, and you get here the image. And here you expose the wafer. Oops, sorry. So the projection system, I keep again, this is the same image. Oops. This is the same image with some explanation. This is the condenser. We call this part a condenser. You take a light source and you make the light reaching the mask in an orderly manner. All the light arrives in phase and or partially in phase, and it hits the mask. So this is very important. This light source is a very important part of the imaging system. You cannot take any lamp. You have to take the lamp and design the lens. There are very well-known light sources that people use in lithography. This is by itself a 1-hour lecture, how to design a light source, but I'm not going to talk about it today. So let's talk about light. Let's consider if a light source, an ideal light source, if it was a point source, then the wave will propagate all over, and it will be like a sinus. So this is like a sinusoidal. If you take an infinitely small light source, it would behave like this. And you know that if you have now few point sources, like then we have 2 point sources, they will have interference. and this is a typical interference from 2 point sources. And you have what we call constructive interference or destructive. If the light is in phase or out of phase, this you learn in high school, that the light has some interference. So if you go again from projection system, we have the light source, and the light source hit the mask. And the mask, because the patterns on the mask are organized in a distance which is in the same order of magnitude of the light, of the wavelength of the light. So if the wavelength of the light is about 193 nanometer, which is the typical light source for the high resolution today, the patterns on the mask, if we talk about 10 nanometer lithography and magnification of 5 to 1, the patterns are 50 nanometers. So if the wavelength of the light is 193 and the pattern is 50 nanometer line, 50 nanometer space, the periodicity on the mask is 100 nanometers. And if the mask patterns are in the range of 100 nanometers and the wavelength is 193 nanometer, it means we have interference. We can't avoid it. The features on the mask are of the same order of the wavelength. They're not much smaller, they're not much bigger, they're of the same order. So we have to take into consideration interference. So how do you study interference? But first, the mask look like this. Typical mask, let's say this is the mask. I just invented the feature, like circles and X, and this is the mask. Typically, it's a glass, and on top of it, we put patterns of material, and this is an example of what you can see here. You have some coating. You put anti-reflective coating, for example, you don't like to be reflected. And this is the side view of the mask, and this is how it looks. This is, by the way, this is the cost of the mask today. The mask in our university is about 1K, but if you go to the industry, this is what you pay for one mask. This is not a small matter. If you do a CMOS process, you have like 20 to 30 masks per one circuit. So you have to expose the wafer 20 or 30 times. You have to print the transistors, print the interconnects. You have NMOS and PMOS, and you have source and drain and gate. You have 20 to 30 masks. And if each mask is this, 150K, you understand that just the mask set is a lot of money. And if you made a mistake, you need to do it all over again. So design mask by itself is something important. Now let's go to interference. Let's say you have a very simple mask, dark, open, dark, and the light is coming. Each point on the wavefront may be regarded as a new source of waves. So practically, if we look at this structure, if the light is coming into this feature, and we look at the diffraction from this opening, we don't get this behavior. What we have, the light is propagating in a circular way. We are generating circular waves, and according to Huygens principle, the propagating light is a superposition of many, many point sources which are organized here. So if we look at the mask, and let's say ideal mask, a typical mask, dark, light, dark, light. Now, this is actually a very common feature in many circuits. If we talk about electronic circuits, if you talk about semiconductor microprocessors or memories, in a microprocessors, usually it's not 1 bit. Typically, microprocessors are 64-bit or 128 bits or 256, which means usually in a normal design, you don't have one line. You always have like 64 lines or 128 lines. So if you look at the features inside many, many circuits, you find a lot of periodic structures. If you look at memories, memories are inherently periodic devices because you have one cell, second cell. If you have like 1 gigabyte memory, you have 1 million by 1 million components organized in a periodic structure. So if you look at the mask of a cell, at the mask of a memory, you see a lot of periodicity. So this is not just a theoretical experiment. So if you have a periodic structure on your mask, you know that according to Bragg diffraction, if you will have the light will go through the structure, but you split it into rays. You have first order going through zero order, first order, you will get propagation only at specific angles which following Bragg's law. P, which is the pitch. Pitch is line plus space. This is the periodicity of the structure. You will get some DC going through here, but you will get one beam going in this direction, one beam going in this direction, and you will get beams propagating. This is a kind of a simulation of what you can see. You have a zero-order beam, first order, or plus and minus 1, plus and minus 2. And those beams, they carry the information of the mask. If you want to reconstruct the image, you have to collect all the beams and combine them together on your mask, on your wafer. So what happens is that if the light is propagating, what you got here is initially you have like what's called a near field. You get some diffraction pattern, which is for very, very short distance. And then you got some, the light gets some shape here, and you get here in the larger distance, we call what we call the Fraunhofer diffraction range, and here we get the Fourier transform of the image that we got here. So if you want to analyze this kind of systems, and you're assuming a fully coherent light, you use a Fourier transform analysis, which works very well. Unfortunately, and I'm not going to talk about it today, the light that we use is not fully coherent because we don't use lasers which are fully coherent. The XML lasers are not very coherent lasers. They have a few hundred modes, so they have some partial coherence inside. So it means they are partially coherent, partially not coherent. Again, I raised this topic just to show you that the life is more complicated, but let's assume that we have a coherent laser. It's not a good idea for lithography because in a coherent laser you can have other defects which we call speckles. Speckle, if you look at a coherent, if you illuminate a field with a coherent light, you will see some dark and white spots, which is called speckles. So it's not a good idea to use coherent light. But for this analysis, let's say that we have a coherent light and we can use the Fourier transform. So what you have, you said that Fourier optics, you can define the transfer function. You can have the image is the Fourier transform of your mask. And the field distribution in the diffraction plane is the special frequency spectrum of the mask function. You define the special frequency, like, for example, 100 cycles per centimeter. If you have like 50 micron line and 50 micron space, the pitch is 100 microns, and 100 microns is 1/100th of a centimeter. So this is 100 cycles per centimeter. So this is called special frequency, and you define a pitch. Remember this value, pitch. Pitch is the periodicity of your structure, because this is a very important parameter when I'm going to talk later how to get better lithography. Because then you can understand that for every system, you can transfer until a certain frequency. When you reach a certain frequency, the performance is going down. The system behaves, there are many electrical engineers in this room, or most of you are EE or some mechanical engineers. The system behaves like a low-pass filter. It transfers all the frequencies until a certain frequency, and then you start to have deterioration of the system because of diffraction. And the periodicity is 1 over line plus space, because we measure the periodicity by cycle per centimeter. Just an example, if you have a single spot, the Fourier transform is a sinc function. If you have a periodic structure, the Fourier transform is a set of delta functions. And for example, you understand that the information is carried. If you take a feature and you take the Fourier transform and you want to reconstruct the image, you have to sum all the components and do the inverse Fourier transform. So this is what the lens is doing. The lens is doing the inverse Fourier transform on the mask. This is the role of the lens. But if we want the mask, the lens, to work well, we need to take all the components. So the lens has to be infinitely big, because we want to collect the first order, the second order, the third order, the fourth. If we lose some orders, we lose information. So what is the smallest lens I can use is the lens that we collect the first order. If we don't collect even the first order, we lose all the information. This is called resolution limit. The lens has to be big enough to collect the 0 order and the plus and the minus order. Because if I collect this, I know the periodicity of the structure, and I can reconstruct it. At least I know what the periodicity. And I'll show you later that this is enough. You don't need to collect many orders of the diffracted beam. It's enough to collect the first one. Just the numbers. If you want to do diffraction, you need to know the refractive index. Air is 1, water is 1.33, a fused silica is 1.46, diamond are 2.4. People use some diamonds for coatings if you want high refractive index. We don't use full wafer diamond. It will be too expensive. But there are technology today to coat with diamond. It's called chemical vapor deposition of diamond. And we will talk about it on the lecture on chemical vapor deposition, on plasma enhanced chemical vapor deposition. Little bit geometrical optics. You have to remember 2 rules. One is the law of reflection, that if you hit, if the light hits with an angle theta I, the reflected light is in theta r, and theta I should be equal to theta r. This is a simple law of reflection. And in Snell's law, if we go from a media with a refractive index n1 to a media with a refractive index n2, then n1 sinus theta 1 equals n2 sinus theta 2. And I go fast because I assume all of you are familiar with Snell's law. So let's talk a little about the lens. If this is the object is illuminated and the image goes through the lens. So the lens sees the Fourier transform of the object, and the lens is performing like the inverse Fourier transform, and we got an image here. So we can define the focal length. We can define the focal point, f. Typically, s is in the range of 2f, and we can define practically an image here. And what we want the image to be as sharp as possible. What we said, we want the image to be in focus. And this is sometimes a problem. And this is why the reason we use very flat surfaces. That's why we make all the high resolution circuits in very, very flat surface. And there is a step in production sometimes called planarization. If I have an area which is a little bit not flat, I put some cover on top of it and polish it to make it flat. So in many steps during the process, you can see a step which seems like a waste of time. Why should I do it? Because I put material, it costs me money, and it also may have some problems. But if I want to get good lithography, if I want to get high resolution lithography, I have to be very flat. So all the image will be in focus, because the image, if the image is not in focus, then I'm doomed. I lose resolution, and then I lose money, I lose my job, and I have to find another business. So there are a few things that I'm going to mention during this lecture. I'm not going to talk a lot about it because it's a whole topic. If you design such systems, you have to understand that every lens has aberration. An optical aberration is a departure from the performance of an optical system from the prediction of paraaxial optics. The optics that we use is called paraaxial optics, which means the lights are, we always we look at the light beams in a reference to a certain axis. We have an axis of propagation. This kind of optical system is called paraaxial system or paraaxial optics. And we have problems. In an imaging system, it occurs when light from one point we assume that all the lights are converging in one point, but sometimes they don't because of some problems. Aberrations occur because of the simple paraaxial theory is not completely accurate. The lenses are not ideal. And aberration leads to blurring of the image. Let me show you a little bit what kind of aberrations. Lens imperfections are inevitable. And as a rule of thumb, if the total aberration induced error is less than 1/10 of a lambda, the effect on the patterning resolution is okay. So if you want to live with this lens, you want to look at the aberrations, and you can calculate. There's a whole field of how to calculate aberration of a system. It's a well-established theory, and you can model it, and you have simulation tools to do it. And if you want to have a lens that you can sell me to do my lithography, you have to show me that the aberrations error is less than 1/10 of a lambda. And the aberration, by the way, for example, I show here a very simple source of aberration called chromatic aberration. You all know this famous experiment when light propagates through glass. Look, if you put this element versus the sun, you see that you break the white light into various colors because the refractive index is a function of wavelength. So how do you solve this problem? If the lens, the refractive index is a function of the wavelengths, we don't want this. I don't know, so x, right? How to solve this problem? If I have a chromatic aberration, which means I use different colors and the focus is in a very different places. So how to solve this problem? Use a monochromatic light, use a laser. This is why we use lasers. And this is why people use also mercury arc lamp, because mercury arc lamp has very sharp resonances because of the nature of the emission from the mercury atom. You cannot use regular sodium lamp or other lamps because you got chromatic aberration. You have spherical aberrations, coma, astigmatism. If you have glasses, I suffer a little bit from astigmatism. The vision in the center is a little different than the sides because of the behavior of the lens. We have to solve this issue. And why do we have to solve this issue? There's a very pragmatic problem. If you go to a company, you don't have one single exposure tool. You have 10 or 20 or 30. And you never know, the wafer can go at step 1 at machine 1, and the step 2 to another machine, and step 3 in another machine. If you're a good fab manager, maybe you want all the wafer will go every time that you need the lithography step, because you're building the circuit. You're building the gate, then you build the connectors, then you build the connectors, the lines on top of it. If you build a circuit, it's like layer after layer. You can make the wafer to go every time through one machine, but then you have to wait, because maybe there's another wafer in line. So if you have 20 or 30 machines, you want every time when the wafer is coming to go to the machine which is the queue is the shorter. So we want all the lens to be the same. And it's not trivial because every lens is made differently and they may have different aberrations and different errors. So this introduces also, it's a practical problem. So the projection optics, you take the Fourier transform, and I will skip all the word because we discussed it already. And you take the inverse Fourier transform, and this is what you see in the image. And this is a better description, because if you have this periodic structure, let's call this line width. This is the line of this dark. When you illuminate, this is blocking the light. The light is going only here, or here, or here, or here. And the Fourier transform of a periodic structure is a collection of delta functions, which we call orders. And order 1 will go with theta 1. Order 2 will go in theta 2. And you can show that P, the pitch, which is the distance here, times sinus theta, is equal m. M is an integer, 1 for order 1, 2 for order 2, etc. So you can calculate theta. So this is called, you are collecting the 0 order, the minus or the plus 1 order. If you want to reconstruct the periodic structure, you need to know at least the first order. If you don't, if the lens is too small, you are losing the first order, and you have no idea what the periodicity of your feature. If you collect the first order, you know the periodicity, and I can show you later that this is enough. If you collect the second order, it's even better. If you collect the third order, it's even much better, but you pay because your lens is bigger. Now, the weight of the length is proportional to the dimension to the power of 3, because you know that weight proportional to the volume, and the volume is proportional to the dimension of the lens to the power of 3. So if you make a bigger lens, it's much heavier, more difficult to make it. So you want to use the smaller possible lamp at the, so probably it's a kind of a trade-off. How big is the lens? And by the way, the cost of a single lens today is in the range of half to $1 million. So it's a very expensive lens, very difficult to make. There are, to my best of knowledge, in the lithography business today, in the high resolution, there are only 2 or 3 companies that know how to do it. And it's a critical component. So you can define a critical dimension. What is the angle that you collect the first order? And we call this a CD. So CD is the minimum dimension in the mask that our optical system can collect at least the first order. So I can reconstruct a periodic structure. So we call this critical dimension, and this is Rayleigh's law for resolution. This concept was established by Lord Rayleigh. He established that the optical system the minimum feature or minimum dimension that the optical system can reconstruct is defined by this equation when we take the first order. So the size of the lens matter. It's not only the size of the lens, it's about the size of the lens and the distance between the lens and the mask. But the distance is sometimes determined by the magnification of the lamps. So if we are working with a certain magnification, we have to keep a certain distance. So if we do all this analytics of the mask, we define a parameter that we call numerical aperture. We say P sinus theta equal to the numerical aperture is the maximum acceptance angle of the lens. So far, I did not introduce, you see, in this analysis, you don't see a refractive index. But if I have inside here, because here I did not tell you what's inside here. So until now, we assume it's air. But if there is another medium here, and this medium is not air, the speed of light in a media is the speed of light in air divided by the refractive index. So here I will have to replace it m times the wavelength inside this media. And the wavelength inside this media is lambda over the refractive index. So I should put here P sinus theta equal m lambda divided by the refractive index. So n times sinus lambda is a factor that I need to, this is my important factor. The important factor is not only sinus theta, and this sinus theta is the ratio between the half size of the lens to this distance, which is the focal distance. We define numerical aperture as n, the refractive index, times sinus theta. And sinus theta is, we take the angle, the theta here is the angle or the acceptance angle of the lens, which is practically tangent theta is half the diameter divided by the focal length. If diameter is d, this is d over 2 divided by the focal length. This defines tangent theta. And if I know tangent theta, I know sinus theta. And we define numerical aperture as n sinus theta. And this defines the resolution. This is the critical dimension should be p over 2 in this case. Another, I will review it a few times because it's an important factor. Let's say we have an illuminator and we have the condenser generating a beam propagating in parallel to the mask. We get here the diffraction. We have the zero order, plus 1, minus 1, plus 2, minus 2. If I collect plus 1 and minus 1, and I will reconstruct the beam here, I will get here a very simple feature. It's not, I started here with a mask, which is very, very beautiful mask. This is like a square, but here I will get here a collection of shapes. Each one looks like this. So the image of this feature will look like this. So instead of having a beautiful rectangular function, I will have something which is smeared. But sometimes it's enough for me to reconstruct the image. Because I know what I know. I have some a priori knowledge. When you design a circuit, we know that the mask is black and white. So even if I get a sinus feature on the image, I can cut it. I put a threshold filter. And what is a threshold filter? It's called photoresist. The polymer is a binary material. When you illuminate it, it's soluble. When you don't illuminate it, it's not soluble. So the photoresist behave like a nonlinear material that converts the kind of soft, not so defined feature, but with the information to the right pattern. So this is the trick. So this is, for example, there are two systems. What are the limits of resolution? Let's say that we have a mask. We have a mask here. This is two wavelengths. Let's say the blue one is with a wavelength lambda 2, the red one with a wavelength lambda 1, and let's say lambda 2 is bigger than lambda 1 is bigger than lambda 2. And because of this, you can see that here we are acceptance. We're collecting the 0 order and order 1 and minus 1. The blue one, it has shorter wavelengths. We collect 2 orders. So this system will have a better resolution. So the shorter the wavelengths, the better the resolution. It makes sense intuitively. So we define the minimum CD as lambda over 2 by the numerical aperture. This is Rayleigh's theory, and I put here approximately, because this is for linear systems and for coherent illumination. And since we are dealing with systems which are incoherent or partially coherent, and the photoresist is nonlinear material, sometimes you can see that people, instead of writing 2, they put here a constant, they call it K1. And this K1 is a fudge number. You can put there anything between 0.2 to 0.5, and you fit it to your machine. You take your machine, you measure it. Resolution is a function of lambda, is 1 over numerical aperture, and you put here some constant which we call K1. So in a practical system, people not use 1 over 2 or half. They use a fudge factor which is called K1. So K1 in lithography is a well-known material. And if there's K1, there's also K2. So what is K1? Rayleigh resolution. Some cases, if you do a circular analysis, you find that it's 0.61 lambda over numerical aperture. In the practical resolution, it's K1 lambda over numerical aperture. I put your K1 between 0.6 to 0.8. But this is an old value. You can put here K1 can be as low as 0.2 today. With the modern systems, K1 can be really aggressive, and I can show you how. By the way, one trick which is, I don't know why people didn't think about it before, but after a few years, somebody came with a very clever idea. If you take this mask, you have the 0 order, 1 order, 2nd order, and if the lens is too small, you are losing the 1st order and you are losing your image because you get only DC. But if you illuminate the mask not straight, but illuminate it with an angle, what happens? You are collecting +1 order and you are losing the -1. But since you are collecting the +1 order, you are collecting the information. So this is called off-axis illumination. And how strange as it sounds, if you, instead of illuminating your mask in perpendicular, but illuminate it in an angle, you get better resolution. Seems like, well, what I'm doing, I'm destroying the image. No, I have 2 diffraction beams, but one is twisted, and if this beam, in this case, this beam is outside, is not collected by the lens, so you're losing the information. But here, the beam is collected, so you're generating the image here. Of course, you're losing some intensity. To be precise, you're losing 50% of the intensity. So what you do, you take a laser which is stronger. Just take a stronger laser, and then you compensate for losing of intensity, but you get better resolution. One of the companies came with this bright idea, and this was like, oh, we can get much better resolution with a better lens. The last thing I want to do before we go to break is the depth of focus. If I take a beam and I generate, if I generate kind of if I want to focus the beam, usually the point of focus is not infinitely small. the wave is propagating like this. And we have an area or region where we have focus. And this distance, which means if I focus, anytime you take an image with your camera, today you use your cellular phone, so you have no idea what is taking a picture. But if you see professional photographers, they play with the lens and everything has to be in focus. And then you know that you have some comfort zone. You are in focus. Even if you change, if I take a picture of you, you will be in focus or vice versa. There is something which is called depth of focus. And this depth of focus, the law is it's proportional to the wavelength, because the shorter the wavelength, the shorter this depth of focus. But you can show that is inversely proportional to the numerical aperture square. So this is K2 lambda over 2 numerical aperture square. And this is a problem, because we want a shorter wavelength for better resolution. But what we pay in a shorter depth of focus. So if you have a photoresist and we illuminate it, this is I intentionally put it into kind of a absurd, but this is your substrate, this is your photoresist. Where do I focus? Should I focus here? Should I focus here? Should I focus here? So I need to know, that the depth of focus will be at the same order of the photoresist, or I will use very thin photoresist, for example. Or there's one company, what they do, they take 3 images. But if you take 3 images at 3 different focuses, you pay, because it takes time. And time is money, your process is slower. But depth of focus is a big problem, which has to be solved. And the shorter the wavelengths, the more severe is the depth of focus, and the more important is the requirement for planarization. That's why 20 years ago, there was no planarization section in the company, and today there's a lot of planarization in every manufacturing facility for high-resolution lithography. So we'll go for a break, and we'll continue with light sources after we collect some light outside. No, one. No, אני אסביר לך את זה אחר כך בהפסקה הבאה, בסדר? הלכתי לאיבוד. Okay, light sources. I'm going to review again and again the business of lithography, how we do it. So I'm trying to simplify it. There are many things that I'm oversimplifying, but this is because we have this class is an overview of lithography. For example, I didn't tell you that a regular lens is actually not one lens. Typically, you have 10 or 20 components, etc., etc. But the concept is that you have a system that you take the Fourier transform or the diffraction pattern, and the lens is doing the inverse Fourier transform. So the shape on the mask is identical to the shape on your wafer, but different size. So light sources, it's very simple. We are dealing with the ultraviolet spectrum, and of course you understand why we use blue light, because of the short wavelength. This is called EUV, VUV, DUV, deep UV, mid UV. If you use a mercury lamp has 3 very useful wavelengths, G, H, and I line. The XML lasers today in the market are 248, 193, 157, 126. These 2 are the 2 most popular. Oops. And if I look at mercury arc lamp, those are the wavelengths that are most usable today. The XML lasers which are popular today are krypton fluoride at 248 nanometer and argon fluoride at 193. Those are gas lasers based on the special behavior of this component. And if I look at, for example, at the spectral, this is intensity of a mercury arc lamp, typical strong one. Now, it's a very powerful lamp, but this is a spectrum of a mercury arc lamp, and this is a spectrum of the XML laser at 248. And you can see that the XML laser is typically stronger and also narrower bandwidth. So these are the typical illumination or the spectrum of XML lasers. Here I show again the mercury arc lamp, because mercury arc lamp has this 436, 405 is 365, but there's also a lot of emission in deep UV. And if you have a stepper in our lab, we have a stepper, we have this machine for exposure, and we have a mercury arc lamp, and we can generate deep UV in our system, but it's a contact print. It's not a projection system. Just to show some characteristics, those are the three most popular excimer lasers that people use for lithography. There are many excimer lasers, but those three are the most popular: 248, 193, 157 nanometer. And you can see that they are pulse lasers, illuminating like 300 to more than 1,000 pulse. This is the frequency is in the range of few hundred pulses per second. The energy of the krypton fluoride is the strongest, and it can generates almost 1 joule per pulse. Those are very short pulses. And one advantage of the excimer lasers is that the illumination is in a very short time. So you can actually move the wafer through exposure, and because the pulse is about 10, 20, 30 nanosecond, practically the wafer is not moving because you illuminate it in a very short time. So you can do exposure on the fly when the wafer is moving. So this is light sources. Masks. Again, I'm going to review it very quickly. This is a very trivial issue. You have all kinds of masks. We have masks which are, we call it dark field, which means a lot of dark areas. We have gratings. We have bright field or clear field when you have dark area, and this is transparent. And this is just a jargon because you have many, many complex masks. But these simple masks are binary. When it's dark, it's not transparent. When it's white or clear, it's transparent. So it's a 1 or 0. And remember this, because light is an electromagnetic wave. And an electromagnetic wave has electric field and magnetic field. They are propagating. So we also have a phase. So in this specific mask, we only transfer the intensity. We don't take care of the phase. And remember this because I'm going to show you later a better mask where we take into consideration the effect of the phase. One of the problems is if you take a square and you print it on the corners, you get some rounding. Because if you remember, we take the Fourier transform of the image, and near corners, we have more high frequency. So in order to correct it, a very simple thing is called OPC, optical proximity correction. You print here a little kind of oversized feature. This looks like a dog bone. And if you print this dog bone, you get this very nice. So it's actually a very simple solution. The only problem with this solution is we assume that this feature is independent of this feature. We assume there is no proximity effect. So this solution is good for small, isolated features. It's not so good for when we have small but close features. But it's actually very popular. The mask itself usually, if this is the mask, another name of a mask is called reticle. If you see reticle and a mask, it's the same. It's another name for a mask. One of the problems with masks is what happens if there's some dust on the mask. If there's some accidental particle or something on the mask, you print this particle, and this is the end of your business. So a very simple solution. You put something which is called pellicle. You put some spacer, and you put here a very, very thin layer of polymer, transparent to light. So the mask itself is covered with, you put some like, you cover, but you cover it with an optical transparent structure. And typically here you purge it. I mean, you flow some air here between, and this is called a pellicle, or hard pellicle, which is kind of a protection over the structure. Yes, question? The sizes aren't dependent on the I copied it from some manufacturers, so ignore these sizes. This is just example of one mask for one manufacturer. So it's, of course, it depends on the wavelengths, it depends on the application. For every number, there's a reason. But please ignore it because I took it from some publication, from some real mask. But this is a very common, I just want to show you how people protect their masks today. Now let me show you how to get better imaging. For example, if we take a mask, this is dark, clear, and we illuminate it. The light is propagating. We got, this is the light. This is the profile of the intensity of the light from this pinhole. This is the propagation. This is the intensity of the light from this. But this is the amplitude of the electric field. Now, what is the total intensity? We sum this electric field. They're in phase. And because they're in phase, I sum them. And this is the image. And you can see that initially I started with 2 holes, but the image is terrible. The image, these 2 holes are too close. They are below the resolution, so they merge. So the intensity of the light on your mask, on your wafer, will look like this, which means you cannot print this resolution. What happens if I put here an optical component? And this optical component, when the light goes through an optical component, there's a phase change. And I designed this optical component that when the light is coming here, and we compare it to the light coming here, this element adds a phase to the propagating light, and this phase is half lambda, which means the intensity is the same, but here the phase is 180 degrees off phase of this. So now, if I want to calculate the intensity is the absolute value of the electric field. So now the intensity looks like this. So this is called phase shift masking, or PSM, which has become more and more popular today because you can, in the mask, you don't only record, the mask itself contains not only the information about black and white, but also you put some phase change. And there are a few possibilities. You can do what's called strong phase shift. This is what I showed you before. Strong phase shift is when you shift by like 180. And by the way, you can put, instead of one phase shifting, you can put 2, 3, 4 phase shifting components. You can shift in 60, 120, 180, or in 45, 90, 135, 180. And you can actually build your image by shifting various phases and reconstruct your image by taking into consideration the phases also. And you can show, by introducing phase into the mask, you can get better resolution, as I showed you before. You can also, for example, do what's called weak phase shifting. You put, instead of putting a dark image, you put here an element which shifts by 180, and you put the mask on top of it. So if you look at the intensity, this is intensity because it's clear. Here you shift it by 180 because of this optical component, and because this is black, the light here is 0. And you can show that if you take this kind of image, you can get much better resolution than just the dark. If you combine transparent and opaque elements and use this phase shifting, you can get you can get much better resolution. And if you really want to go to the extreme, you can also record the phase. This is called pixelated phase shift mask. Not many companies are using it. It's extremely difficult to design it. But in principle, let's say you want to print this feature, you take this structure. In every component, you modify the phase or modify the intensity. So this is your mask. And when you print this mask, you get this, which is identical to what you want. Because if you don't do this, you will get less resolution. To summarize this concept, again, this is 5 minutes about phase shifting mask, but you have to believe me that it is working. But the idea is, instead of just making a mask dark or clear, transparent or not transparent, you can also introduce phase. And for every pixel, you can do you can play with it, and you can control or engineer your wavelength, your wavefront, that on the wafer, when you reconstruct your image, you get the best resolution. This is called pixelated phase shift mask, which is like the state of the art of mask today. And I'm going to talk about, if you really want to invest in doing it, those masks are unbelievably expensive, especially when you do it for very complex circuits. You don't use it, you don't just use it. I'm going to talk about immersion lithography, which is how to improve the resolution. OPC, we talked about it. Phase shift mask, we talked about it. Off-axis illumination, we talked about it. Resist trimming, we didn't talk about it, and I'm going to mention it. And about double exposure, which I'm going to talk about it. So we are now finished the first part of the lecture. We are going like to more complicated structure. But before we go to more complicated structure, let's talk about the photoresist. So I'll talk about photoresist, about modeling, and about something which is called focus exposure matrix. Somebody asked me during this break, how do I measure it? How do I know that I'm in focus? So I can answer, okay, I know if I'm in focus if I get good image, but this is not a good answer. So I really want to know during manufacturing if I'm in good condition, if I'm in focus. So one very simple way to do it, and I'm going to talk about it, is take some test structure, like lines with specific structures or something that you know, and print it and move the wafer up. Print again, move the wafer up. So you can actually, you're changing the distance between your wafer and your lens. So at one point, you're going to be at the best focus. And the other point, you will be below focus or above focus. And then you go to electron microscope and look at the results. At one distance, you get the best resolution. Because what happens if you're out of focus below, image is blurred, you cannot print very narrow lines. If you're above the focus, again, it's blurred. So this is called exposure matrix or exposure focus matrix, which means you change your focus, but since you're running this experiment, usually what people do, they do 2 experiments in one shot. They run one line when they change the focus for a certain intensity of light. Then run another line with a slightly bigger, more light. Another line with more light. So you can generate a big matrix where one axis is the focus and the second axis is the intensity. Then you go to electron microscope, spend a few hours, or convince somebody else to do it for you, and then you know which are the best conditions. And I'm going to give you more information now about how to do it. And by the way, you can model it. There are today, everything that I talked about it today can be modeled. There are optical simulators. I'm going to talk about photoresist. There are photoresist simulators. So everything can be modeled. So typical, there are 8 steps of photolithography. You take your substrate. Let's say you want to put photoresist. Typically, people put hexamethyl disilicon or other materials called a primer. If anybody of you paint a wall, you know that before you put the paint, you put some base to get a good adhesion. So typically, you don't just put the photoresist on your substrate. You do some treatment. You spin coat. You put a drop of photoresist. You rotate it, and then you got the spin coating, and then you do some heating to stabilize the polymer. You expose it with your exposure system. After exposure, you do some annealing, and I will explain to you why we heat the samples after the exposure. Practically, you got some photochemical reaction here, and you are actually, by heating it, you accelerate or you finalize the reaction. So it's not just for fun. You develop it. I'm going to show you what is development. Then another temperature cycle to further stabilize it, and then you develop it. Develop means you remove the parts which you're not interested. So what this is the photoresist. Typically, this is a solution, and inside the solution, you have a solvent, gives resist its flow characteristics, which means it's practically you put it in a solvent to make it a solution. Inside, you have another component called resin. It's a mix of polymers that's used as a binder. This is the material that gives the polymer its strength. Then you have the sensitizer, or light-sensitive materials, also called PAC, photoactive compound. And then you have additives. Additives, this is something nobody tells you what it is, but this makes it smoother, nicer. This is usually a trade secret. But we're going to talk today about the binder and the sensitizer or the photoactive compound. As I showed you before, let's say this is your substrate, this is your polymer, and the polymer is this structure, and inside the polymer we have photoactive compound. If you have this material, it's a very stable material, unexposed, it's very, very strong, very insoluble. You put it in solvent, it's stable. It's like Formica, very strong polymer. When you expose it, you actually break the photoactive compound. Then this material becomes soluble. Then when you dip it in a base, typically potassium hydroxide, sodium hydroxide, tetramethylammonium hydroxide, any hydroxide, this becomes soluble. And it becomes soluble because this photoactive compound, when you illuminate it, it practically generates acid. And this acid, you learn from high school. What happens when you take acid and a base together? What happens? If you mix acid and a base, what you generate? Salt. And you just have to design the reaction, and not eating salt. It's another kind of salt. But you generate, because this becomes acidic, and you mix it, if you put it into a basic with a pH of 12 to 13, this becomes soluble, and then you got this very nice feature, very nice cover, and this is inside is open and outside is covered. Typical photoresist, I couldn't get the better image, but it's going like this. If you take this polymer and you look at the absorption of this polymer, before exposure, this is the absorption of the polymer. It's a very strong absorber because it contains a photoactive compound. Photoactive compound is a very strong absorber. We designed this molecule to absorb light as much as possible and to break and to generate the acid. And after illumination, this is the absorption of the photoresist. You can actually break it into two components. The absorption coefficient inside this material is proportional to M. M is the amount of the photoactive compound. And this amount of photoactive compound, we say before exposure, M equal 1. And we normalize it. M equal 1, which means this is the total number of exposure as I have in the beginning. And after very, very long exposure, I break all the photoactive compounds, so M equals 0. So M is the relative amount of the photoactive compound. And as we illuminate it, practically, the photoresist initially is red. Why the photoresist is red? If I illuminate it with white light and the material absorbs blue, the color is red because red is reflected and blue is absorbed. So this is why photoresist, if you take a photoresist and it's not red, it means something is wrong. Because photoresist, because it's a very strong absorber, and the red, it should have like a color, a reddish color. Sometimes yellow, sometimes different, but it's usually red. But after exposure, it becomes transparent. It's not absorbing strong light here. So this is, we usually, we always say that if you have enough points in the line, you can always put a straight line if the pencil is thick enough. So what we say, we linearize it and say the absorption coefficient is proportional to the amount of the photoactive compound. plus B. This is an approximation because normally it's a polynomial and you can, it's more complicated, but very simple approximation and very good approximation is to assume that the absorption coefficient is equal to A, M plus B. So this is called the ABC model of photoresist, where I can describe the photoresist by three components, A and B for the absorption. So this A, the coefficient A is a very strong function of wavelength, very strong absorption here. And B is the absorption of the rest of the material. And usually, since we expose, this is for I-line photoresist, exposure is about here, 365, this is about here. We see that before exposure, it's a strong absorber. After exposure, it's a beta absorber. But this photoresist is useless for ultraviolet. Because if I want to use this specific photoresist for ultraviolet, it's not absorbing, it's not light sensitive. So every photoresist has to be tailored for the application, for the light source that we use. And the positive photoresist mechanism is very simple. This is the polymer. You have the photoactive compound. The light is breaking the photosensitizer. So initially, it's a very strong absorber. But after illuminating, it becomes transparent and very highly soluble in the liquid. To make it more efficient, people found out that you can actually accelerate this process. Instead of putting a photoactive compound, people figure out that the chemistry is practically you illuminate the photoactive compound, it becomes an acid, the acid reacts with the base, and the material becomes soluble. So they say, instead of just this simple reaction, let's put here something called photoacid generator. It's a compound that instead of one molecule generating one proton, every molecule generates many protons. This is called chemical amplification. But again, the principle is the same. This is a photoacid generator. I illuminate it, it generates protons. And if I have H plus and I dip it in a basic solution with hydroxyl ion or H minus, it becomes soluble and I get the same effect. It's a positive photoresist. And this is what most of the companies or most of the applications today, and I'm going to show you later why this gives you better resolution. It's not only more sensitive and also responds to weaker light because you have amplification. You can get the same result with much less photons, but it's also with better resolution. So if you use chemically amplified deep UV resist, and I introduce all these jargon words. This is called deep UV. It's just history because in mercury lamp, people use UV, ultraviolet. So the shorter wavelengths, people call it deep UV or DUV. The resin is a phenolic copolymer. The photoacid generator generates acid during exposure. The acid generated in exposed resist area serves as a catalyst to remove the resin protecting group, which means I go back, you illuminate, the photoactive generator goes some reaction, you heat it after exposure. During the heating, you generate more protons, you accelerate the reaction, and then the exposed area of the resist without protecting groups are soluble in aqueous developer. So this accelerates the reaction. So how to model the photoresist? The model is very simple. You say the optical image interacts with the material. And we have three components, matrix, solvent, the photoactive compound. So we can define, first, M will be the photoactive concentration. You can take it in moles per liter or atoms per centimeter cube, depends on the units that you use. And we normalize it. Say M is the number of molecules as a function of time divided by the initial number. I want to remind you that when I illuminate the photoresist, I basically break the photoactive compound. So this number M is going down. I illuminate it with a lamp. The lamp has intensity. The intensity typically is in watts. How many watts, what is the power intensity per unit area? And I defined energy, which is power times time. You know that energy is power times time. So if the intensity of the light is watts, if watts times second will give joule. So typically, and we normalize it. Typically, we take the intensity as joule per centimeter square. Now, why I'm doing this? Because the energy is what's important. It's not the power. If I illuminate with 1 watt per 1 second, or half a watt per 2 seconds, or 1/3 of a watt for 3 seconds, theoretically I should get the same, right? Because I illuminate with the total energy is the same. So let's think about it. It's actually, the measure is not the power. The measure is the energy. How much energy I put into the polymer. And what we say that the number of molecule M is a function of D, of the dose, not as a power, but if I illuminate with a certain power at a certain time, I put a certain energy. The energy is related to the number of photons. So one number of photons breaks one number of chemical bonds. So the number of the concentration of the photoactive compound is a function of the dose. So the kinetic is very simple. We illuminate, we destroy the photoactive compound. So we can define the dm over dt is proportional to the light the light intensity I. More light, we break more. Less light, we break less. But dm over dt is also proportional to the number of molecules, because if I destroy 10% per second of the molecule, and if I have 1,000 molecules, I destroy a certain number. If I have more molecules, I destroy the absolute value of the number that I destroy is proportional to the number of molecules, because the interaction is between the light and the molecules. So the composition rate of the photoactive compound is also proportional to m. And C is a proportional function. The second is that it's called Beer-Lambert's law. It's a very known law in physics. It says that the light absorption in the resist, the absorption of light per unit length, is proportional to the light intensity. I illuminate more, I absorb more. I illuminate less, I absorb less. But it's also proportional to a constant which I call absorption. And this absorption is a function of AM plus B, as I showed to you before. This AM plus B is called absorption. So I have two equations. One equation is dm over dt equals CIM, and the second equation is di over dx. X is the vertical propagation of the light inside the photoresist. And these two equations, these are two coupled nonlinear partial differential equations. If I solve it, I can solve for m. The unknown is m. I want to calculate m as a function of distance. Because if I know m, I know the properties of the photoresist. Why? Is because of why? Because the dissolution of the photoresist is a function of m. When m equals 1, it's not soluble. When m equals 0, it's soluble. And the question is, what is the ideal number of m? Should I reach half, 20%, 30%? There's a certain value that below it becomes very soluble. And I'm going to show you that it's difficult to get analytical solutions. But I want to get some insight in this model, so we'll invest like 5 minutes in this. It's very short. Practically, you have the photoresists are based on a polymer called Novolac, which is very common for eye-line mercury lamp exposure system. And practically, the photoactive compound, when you illuminate it, you generate an acid, and this is called the latent image, because when you illuminate, you generate m. M is a function of the distance from the surface, but m is also a function on this dimension, because areas which are dark, m is 1 all the time. When areas which are illuminated, m is going down. So m is a function of x, y, and z inside the polymer. This is called latent image. you represent the optical image by the concentration of the photoactive compound M. And when you develop it, you expose the image from the latent image. In a deep UV resist processing, you have the photoactive generator. This is the typical wavelength. And after the exposure and after the heating, you are generating the compound, also a latent image, and the amplified photoresist induced during the exposure. So this is practically you are illuminating it, you are breaking the photoactive compound, you heat it, and the PB is a post-exposure bake. I forgot to mention it. You heat it, you break a lot of the photoactive compound, you heat it, so you illuminate it, you bring the photoactive generator, you heat it, then you generate the acid. And this generates your latent image. So the next step is development. Let's do a simple exercise. Let's assume, I do it quickly, and I will be very happy to answer questions during the break. Let's say this is your function of intensity. This is y lateral distance. And this is your image, I as a function of y. And the red one will be the intensity of the light inside the photoresist as a function for the distance. I want to look at dm over dy. I want to look at how the latent image also is a function of y if I know I shall y. Now, there's no analytical solution. So let's assume a very simple photoresist with constant absorption. There's no analytical solution. In a normal, let's go back, in a normal equation, the absorption is equal AM plus B. And there's no analytical solution. So I want to show you just an approximation. So let's assume it's constant. If this equation is constant, then di over dx is constant times a times I. And this is a classical first order differential equation. And the solution is m is equal E minus CIT. So I take this equation, C is constant, I is constant, so the solution becomes very simple. This is the first order. The two equations become very, very simple. This is m of t, E minus CIT. So let me now take this derivative. dm over dt is exponent that remains the same, times the internal derivative di over dt times ct. Now if I manipulate a little bit these equations, minus ct is actually ln m over I times di over dy. And what I find out that if the image is I of y, the latent image derivative is proportional to m ln m times di over I. Which means if I know the light intensity, I can guess the contrast of the latent image. But interesting enough, the contrast depends on something which we call ILS, image log slope. I see here that the derivative of m versus y depends on the log slope of the intensity, not on the absolute derivative. Because we got here some m times ln m, which forget what it is, but we see that dm over dy is a function of di over I divided by di. And we call this number ILS, image log slope. And the reason I'm mentioning it, because people found out that the quality of the image or the quality of the results depends not on the quality of the image, but on the image log slope. The better the ILS, the better this function, the better this contrast. The better this contrast, the better the slope, the better is the latent image, because the derivatives are steeper. By the way, we can calculate this number, and we see that this function surprisingly has a maximum for m equal 0.37. Please prove it. So ideally, if I want to get the best latent image, I don't need to illuminate until m equals 0. It's enough to reduce the number of photoactive compound to about 1/3 of its initial value. Because initially, m equal 1. As I illuminate it, concentration goes down, down. You don't need to destroy all the photoactive compound. You have to go to about 30%. And people today assume that the best image is when m is about 0.2 to 0.5. Why am I showing you this? Because the next step is the dissolution rate, or what we call development rate. Development rate is you put the exposed polymer in the developer, which is typically a basic solution with a pH of 12.5 or 13, sometimes even higher, and it's soluble. Now, here, it's not soluble, because here we expose it, and this is I call it x is 1 minus m. Here, x equal 0, which means m equal 1. Remember, as I told you, when m equal 1, the photoresist is not soluble, very stable. M equal 0.1 is not soluble. M equal 0.2, it's a little bit soluble. The solubility for this specific photoresist, this is IBM APXC resist. If you go to, you Google it, you get, it's a commercial product. You see the solution in the standard developer is 2 nanometer per second, which means if I want to remove 1,000 nanometers, I have to dip it like 500 seconds. As m is going up, this solution rate becomes faster and faster. Here, it's about 50, 70, 60, 50, 70 nanometer per second. So if I want to remove 1,000 nanometer, I need only 20 seconds, which is a very reasonable number. So this is a theoretical, measured, what we call development rate. Now I'm going to show some slides very quickly because we are not going through this theory. If you want to simulate it, there are two options. One option to take this function, approximate it with a polynomial, and put it in your software, and because we know m, you remember from the previous analysis, we know the intensity of light. We solved the two equations. We found the concentration of the photoactive compound. And since I know the photoactive compound concentration, I know the dissolution rate. So I can calculate how much time I need to remove the photoresist. I'm not going to give you, if you want to learn more about this, and I spent a few years on this project many years ago, there are analytical functions to fit it. I'm going to run quickly through this. I'm not going through the few models which are accepted. If you want to know more, please, I put you a list of papers, which is the theory of exposure and development of photoresist. And today, this theory is very well established. You can even buy a simulator, and we have it here if you want to use it. It's a possibility. If you work for a company, probably you have it in the company. And by the way, many years ago, some people in the University of Berkeley University, wrote their own code. So it's not impossible for students to write the code because the equations are not so complicated. You can solve it with COMSOL or MATLAB. It's not such a big deal. The big deal is to get the right parameters of the photoresist. And I go back a little bit. For example, this is the IBM photoresist. When you buy the photoresist, they give you the A, B, C parameters and all the parameters for the development. So if you want to simulate it, you have to call your supplier and tell him, please give me the parameters. And if it's not, and if he's a serious supplier, they will give you the parameters. So this is the initial papers. The software, there are two available. If you want to simulate it and you don't want to write your own code, there are two. One is called the ProLith. ProLith, which is now it was purchased by a company called KLA Tencor, and you can buy it, you can get it. It's a very, very powerful software that everything that I showed you before, including the image formation and the diffraction, everything. And you can actually simulate everything that I showed you before. Or you go to Berkeley, the work of Bill Oldham and Andy Newreiter and Sharad Nandaukar. all this group. They published it 1979. And it's available on the web. I think it runs on Unix only. I don't think it runs on a PC, but maybe I'm wrong. But it's available, and it's a freebie. So we have this result. We take this photoresist, and we look at the thickness of the photoresist, and we find out that if we do one, this is units of millijoule per centimeter square. For 1 millijoule, nothing happens because I did not destroy enough photoactive compound. I see that I go to 10, nothing happens. Not enough energy. But as I increase the energy, remember, I destroy more and more photoactive compounds, so the system becomes soluble. So the thickness of the photoresist goes down until I destroy so many photoactive compound molecules, or I generated acid with the photoactive generator. And I put it in the solution long enough, so I remove all the photoresist. So I can generate a curve which I call thickness versus dose. This is the most important curve for a photoresist because this tells me that I need to at least, this is 10, this is 100, so this is about 50 or 60 or 40. This is the critical dose. And this is E0, the resist removal threshold dose. And this slope, it's called the contrast of the photoresist. This is the material contrast. It's not an optical contrast, it's a material contrast. And we usually look it as in the semi-log. This is linear, this is a log scale, and we define the slope in the semi-log scale. This slope is called contrast. And you want this slope to be more than 1. You want it to be, but there's no need, I mean, the better the slope, the steeper the slope, it's better, but there is some practical range. This is a result from the simulator. This is printing a contact. This mask was, this area is black around, and this is clear. So this is, you see the mask above here, and this is kind of a sketch because you remember, we have, between the mask and the wafer, we have all the optical system. So the optical system generates the image here. The light propagates down, and this is a contact. So this is a metal. So you got the light being reflected. So what is being generated inside the photoresist? How do you call when you illuminate and the light reflected and you're generating? What's the name of this? Standing waves. I generate a standing wave inside. Now, if this is a metal, what is the density? What is the energy? What is the electric field intensity on the surface of the metal? This is a classical equation in Introduction to Electrical Engineering. This is not even, this is second-year class. 0, exactly. So what is the light intensity at the surface of the metal? 0. So what is the concentration of the photoactive compound at the surface of the metal? Doesn't matter how long I illuminate it. 1. Which means I'm going to have a big problem at the bottom. I will always have a very, very thin layer of photoresist which contains some photoactive compound. So one option is to illuminate. But another option is to live with it, for example. And you can play. This is, by the way, this is the this is the latent image. And this is after development. This is because now you put in developer, this is fast developed, slow, fast, slow, fast, slow, fast, slow, fast, slow, fast, slow. So you get the image of the image looks like this. This is the shape of the photoresist. It will look like this. We got a little bit at the bottom. So one option is after you manufacture this, you go to a process called DISCAM. You take the whole structure and you put it into oxygen plasma. The oxygen plasma will etch the bottom, and this is called a discount process. You solve this problem. There's some other solutions to this. And by the way, this is a system with numerical aperture 0.5 and sigma 0.8. I didn't tell you about sigma because it's a very complicated issue, but I'll say one sentence. The light of the illumination system can be coherent, can be non-coherent, or can be partially coherent. Sigma is the figure of merit of partial coherence. And I'll stop here. If you're interested more in this, it is a very heavy matter. It will consume too much time of this lecture. But sigma is the measure, is the number which determines if the level of incoherency. And people found out that the best resolution or the best results are not for fully coherent light and not for fully incoherent light. The best results are for partially coherent light. And again, this is beyond the scope of this lecture. If you want to learn more, I will be more than glad to show you how to calculate it. So this is a kind of a standing wave effect on the photoresist. We got a standing wave and a few ways to solve it. One way is to put anti-reflective coating. You put a layer, and there are a few options how to do it. You can take a material which absorbs the light or material which generates a negative interference. But practically what you do, this is called, some companies call it ARC, anti-reflective coating. Some companies call it BARC, or backside anti-reflective coating. Either way, what you're doing, you prevent the reflectance from the substrate, so you don't have standing waves. What is the penalty? This is first, less power. Second, it's another process. It's another step, and since lithography you have like 20 or 30 steps, it's another probability to get some defects. But in some cases, there's no choice. No, you need to do it. So, and 2 more slides, then we go to the break. You can also heat the photoresist. When you heat the photoresist, what happens? You have diffusion. So the molecules will start to diffuse, and then you practically destroy this beautiful, unwanted structure. You get a much, much better shape. So after a post-exposure bake, it minimizes the standing wave effect because you are introducing diffusion into the structure. The last issue is everything I described to you today is assuming that you have a lot of material. But when you deal with extremely narrow lines, and then the polymers has a certain size. The polymers, the monomers of the polymers are in the range of nanometers. So when you are dealing with a line which is few nanometers, and the polymer itself is of the size of nanometer, then suddenly what is called the roughness on the side of the polymer, if you look at the side of the polymer, this is kind of schematic image, the molecules are not always, what is a polymer? Polymer is made of many units which are called monomers. And when the size of the monomers is in the range of nanometers, you can get on the side of the polymer roughness, which is measurable. So this is called line edge roughness. And then all the models we assumed so far are continuous, but maybe the continuous models are unable to simulate the roughness. We have to go into different kind of modeling. So we go to break, and then characterization and process windows, and ultra-high resolution lithography. Tov. Okay, let's continue. Okay, let's continue. 2 quick issues, and I'm not going to spend a lot of time on this. Is characterization and process window. As I told you before, you can do an experiment when you expose the wafer in many, many doses and do it many, many focuses, and you find in your mask all the lines with the same width. For example, in this specific experiment, this showed the line, along this line, for this specific experiment, for this specific photoresist, for this specific tool, for this specific mask, etc., etc. This is the line of 0.25 micron, 0.225 micron. This is the line for 0.25 micron, and this is the line for 0.275 micron. And this is a typical result. Typical result is there's only one line width where it independent of the focus, or this is the focus between minus, for this specific system, which is quite an old system, we got the same line width, independent of the focus. So this is called a focus exposure matrix, and this is how you characterize the photoresist. And you define a working window. For example, you can take your results and take your photoresist and take a cross-section in electron microscope. Photoresist can look like this, and you can define an optimal focus, a negative focus, positive focus. There's many things you can define, but let's move on. I will not spend on the profile. I would like to spend 1 minute on what we call overlay budget. Until now, I described only single mask exposure, and I showed you how to model it, etc., etc. But usually you have another effect, which is called overlay, because when you make a mask, you generate the source or drain, and the next mask is the contacts, and you have to align the mask. So let's say we have the blue mask, and inside this blue mask, I need to fit this gray mask. So this is perfect overlay accuracy. And if you have a problem in registration, I want you to remember the term registration. You have registration between the masks. And it's a mechanical error, or optical error, or mechanical error because of how you align them. And there is a process called alignment between masks. I'm not going to show you how to do it. It's a very difficult issue which involves optics and mechanics and electrical engineering, because you need feedback, how to monitor it, and it's a very complicated process to keep. And this is called overlay budget. It's a shift in registration. For every step, you have an error. You have to calculate it and know it. So this you have to remember. Now, we finished the regular lithography and how to make it fast, how to increase the resolution. I'm going to show you 2 techniques how to improve resolution. One is called double patterning. Double patterning is based on the very, very simple concept, which is not so simple to apply. Let's say you take a mask and you put, instead of, I'm going to show you two possible steps. The first step is LE or litho-etch, litho-etch. This is called LE process. This is your silicon wafer, and then you have 2 masks on top of it, and then you put the photoresist. Now, instead of printing the photoresist with a periodicity of P, you print twice the periodicity. Sorry, twice the dimension. So instead of putting, let's say you want to do line of 100 nanometer, you put the lines with a distance of 200. So you print only half your image. But because now you're working with a lower resolution, you can use your machine to do it. Then you etch this hard mask number 1, and then you print again the second half of the mask. So instead of printing the mask at one shot, you're printing the mask twice. Instead of printing one mask with 1 resolution, you print 2 masks with half the resolution. Sorry, with twice the resolution, or with twice the dimension. Okay. So instead of printing 100 nanometer, for example, line in space, you print twice 100 nanometer line, but 200 meter space. And because, if you remember, the resolution depends on the periodicity, not on the line width. So this is called litho-etch, litho-etch, or you can do litho-freeze. This is your hard mask. Hard mask is kind of a mask which you sacrifice. So you put the photoresist, print half of the mask, then you print the second half, and then you have the high resolution when you print twice with a lower resolution. So this is actually a very interesting concept, and this is just, I'm not going through the steps here, but in a normal mask you have one exposure. In a double exposure it's much more complicated. So, but this is how it looks. I took this image published by MIT. Let's say you want to publish this structure. So instead of printing everything together, you want to print this high resolution mask. You actually print, for example, double patterning. Instead of printing this structure at one shot, you print it. This is the desired structure. What you do, you print it in a few steps. You print this one and this one, so you print it in 2 steps. But I will not. Let's skip to the next one. Why I'm doing this? The reason is that the current tools today, if you want to print 22 or 18 or 40 nanometer, you're above the resolution of existing tools. So by using this technique, you can use the same tools, the same photoresist, and print twice the resolution. So you can keep the technology base for a longer time. Oops, I'm going backwards. So let's keep these slides are not so successful. If you remember K1, K1 was the number which relates resolution to wavelengths. We said the resolution is constant times lambda divided by numerical aperture. So this is K1 as a function of the technology. Today we are about here. So 20 years ago, we improved K1 by improving, going from I-line photoresist to excimer laser. OPC, optical proximity correction, krypton and argon fluoride laser. And if you do double exposure, double patterning, you can get K1, which is in the range of 0.2. Okay, so this is one step. And again, I'm running through this. I just want to bring to your attention that technology, which is called double patterning lithography, which is a lot of work, but it's working. Another option is to use what we call immersion lithography. In a normal lithography, normal system, we have air in the system. We have the lens, we have the mask, we have the wafer. Everything is in air. You can, instead of using air, here you put liquid here. You put electrolyte. This is called immersion lithography. Why do you do it? In immersion lithography, we have your illumination, we have the mask, we are collecting the here I put like 2 elements of the mask, and you're collecting, the lens is collecting all the waves, and you are collecting the light on the wafer. But between the second lens, between the lens and the wafer, we have water. And water or other liquids have a refractive index higher than 2. Now, if you remember well, the resolution is proportional to 1 over numerical aperture. And numerical aperture is refractive index times something. So if I increase the refractive index, I increase the numerical aperture, and I can improve the resolution. But let's show a little bit the mathematics of it. Let's say immersion lithography principle, the effect of liquid on the numerical aperture. Now, numerical aperture is n times sinus of the collection angle of my system. So let's say we have a dry lens, numerical aperture 0.23, and this is the quartz lens. Refractive index is about 1.56. So this is, we are collecting 0 order, first order, second order. So first order is, first order is collected, but we are missing the second order because when the second order hits this surface here, it's beyond the critical angle, and the reflection, what happens, it's not collected. And you can calculate if you look at, if you know the radius here, you can calculate that you are collecting with a certain angle. If you put here a liquid, and in a liquid you put here this kind of lens, because of the higher refractive index, the angle here is lower. Because according to Bragg's law, n sinus theta is constant. So if n is higher, sinus theta is lower. So the angles here, if here the angle is sharp, if you calculate the angles here are lower, and you're collecting more beams. So the resolution is higher. So the higher spatial orders can be coupled, and depth of focus also can be improved relative to the same dry. So by putting here a liquid, you are improving the resolution and still using the same machine, but changing the lens. So why do immersion lithography? You can use the same light source, same optics, same optical coating, no new atmospheric control, similar resist chemistry, no new mask technology, existing optical designs. Only the back side of the lens has to be changed. You have to introduce fluid there, make sure you clear the fluids, and make sure if there are bubbles to get rid of bubbles, etc. So this is called immersion lithography. And it's actually, this is, if we compare again, this side is a regular lithography when you have air. This side is immersion lithography. We have the first order, second order, third order. What we see, because at a certain, if we put here this interface, at a certain condition, because here the refractive index is 1, and here it's 1.56, we are above Brewster angle, and we got complete reflection. So we are collecting 0 order, -1, -2. Here we put water or other liquid, and then we can collect more orders, and we can get better resolution. Remind you, numerical aperture is n times sinus theta. Resolution is k times lambda divided by numerical aperture, and depth of focus is k2 times refractive index n lambda divided by numerical aperture square. So I improved the resolution just by putting water. So and you can combine it. You can do immersion lithography, and you can do double patterning. So each one can contribute. This is how you can take a 193 nanometer wavelength, 193 of a excimer lasers, and print 22 nanometers or even less by combining double patterning and immersion lithography. By the way, nothing comes without cost. You can have bubbles and water stains. You can print particles, because the liquid also can carry some. So there's a lot of new problems from immersion lithography. So until now, I showed you the very advanced optical lithography. What I want to show you now that there are other techniques, because this class is also, we talk about micro technologies. The technologies I described in the last 2.5 hours are related to the mainstream silicon and manufacturing. And today in silicon manufacturing, the people print down to 6-7 nanometers. So this is serious. But this is, I would call it taking the technology to the edge, taking to the optics, to the regime where it really reaches the edges, reaches the edge, goes to the limit. But there are other methods. And I'm going to show a little bit other possibilities. And if we summarize what are the lithography challenges, this is resolution, 0.1, 1, 10. This is year. So I took this from Intel. They put it on the web for one of the publications. In 1980, people print about 0.35, 0.5 nanometer. And then they used I-line, and then they switched to excimer lasers, and initially they went to 130 nanometer, and this is 130, 90 nanometers, 65 nanometers. So 1980 is, my mistake. 1980 is about 2 microns. 1990 was about 1 micron or less. 2000, we are in the range of 1,000 angstrom. And now we are about 225, 215, 216. We are printing something in the range of 10 nanometers or 1,000 angstroms. But if you look, this is the trend. The blue line is the trend of the dimensions of the chip. But the wavelength of the sources goes down from, this is 436 nanometer, 405, this is the excimer laser, 248, 193. You see that the wavelengths change by a factor of 2, by the dimension change more than a factor of 100. And this is because of going to immersion lithography and double patterning and better machine and better photoresist. But we need something shorter. We need shorter wavelengths. And one of them is called EUV. So I'm going to talk about next generation lithography, which is still next generation for quite a long time. It has some economical, material, technical challenges. And people say that NGL, or which is called next generation lithography, is like never good yet lithography. I don't know. You never know what will happen. So one way to if you want to get better resolution, make it shorter. Make a shorter wavelengths. So there is a technology today, and I'll show you how to do it. You take a light source, and this light source, the exposure wavelength is 13.5 nanometer. And these light sources, which is practically soft X-ray. It's something which is shortened than ultraviolet and longer the wavelengths. It's kind of, you can call it extreme UV or you can call it soft X-ray. Depends which direction you come. Because typical X-ray are in the range of nanometers. So if you take this light source, and instead of using, it's very difficult to make lens for these wavelengths, because most of the materials absorb in these wavelengths, but you can make reflectors. So instead of using lens optics, you're using reflective optics, optics which is made of mirrors. And you take mirror, 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 mirror. If you do it right, you can project your mask. You put your mask here, and you can project your mask using this system. So theoretically, because you're using a 13.5 nanometer system, you can print much, much shorter and smaller features. So the two technologies today which are competing head-to-head are the deep UV, which I showed you before, laser source, and scanners. They can either all glass optics or mostly glass optics. You can have numerical aperture today up to 130 in immersion lithography, and they operate in air. EUV, you use it, it's an incoherent light source. This X-ray is completely incoherent light source. The optics is mostly mirrors. The numerical aperture is about 0.25 or less, and EUV scanners are completely encased in a high vacuum system. So it's still a challenge how to make mirror optics, how to make the whole system is in vacuum because air absorbs X-ray. So it's a very expensive system. By the way, it's very interesting, the light sources at 13.5. And this is just as an anecdote. This is a derivative. If you remember, there was have you heard about the Star Wars initiative of the American government? It's people try to make sources of very strong sources of X-ray that can maybe destroy satellites in space. So people developed extremely light, extremely efficient sources for X-ray. One of them is called the gas discharge source. When you take gas and you take like metal, you ionize it, you make a droplet of the metal, and by a combination of magnetic field, you generate a plasma, and the plasma converts to a singular point. So all the material is kind of converging to a singular point and explodes. And during the explosion, you generate a very intense X-ray beam. So this is called gas discharge source. And this is a typical wavelength of a xenon discharge. You take the gas xenon, you ionize it, you by kind of a magnetic field, you converge all the gas to one point when the atoms reach a critical value and explode. And this is the typical spectrum of a xenon discharge lamp. The other alternative, there are two light sources today. One is called the plasma discharge source, and the second one is you take a few lasers and you focus all the beam of the laser to a certain point in space. You inject a droplet of material into this point, and you put a lot of energy into a very small droplet of metal. You got an explosion, and you generate very intense light beam. This is called laser-produced plasma source. And those two sources are commercially available. They are not cheap, but they're available. So a generic EUV system, you have the light source, you have the optics, it's typically reflection optics. You have the light source, you're collecting the light from a mirror to your mask and then to the wafer. And you illuminate your wafer using extreme UV. And such system exists. They are still not in manufacturing because of cost, because of material problems. It's very difficult to make the mirrors. It's very difficult to find new photoresist or X-ray resist for this material. So it's still in development stage. If you go to some universities, many universities like SUNY Albany, Berkeley, some universities in Europe and in Japan, there's very intense research in this field, because if this will work, then we'll have a commercial system to print nanostructures in a very large scale. You can use just simple X-ray. For example, this kind of system, like the same system that you have in a dentist case. If you go to your dentist, God forbid, but if sometimes we go to dentists, they have this machine. They have a rotating disc of metal. You take electron beam. The electron beam hits the metal and generates X-ray. And you can generate this X-ray. The problem with this kind of sources that the beam, the X-ray is coming from a point and the beam is not parallel. So if you put the mask here, the shadow in the center is different than the shadow in the side. And the masks, the problem is that this kind of mask is very difficult to make big masks, because in this kind of a system, the magnification is 1:1. So if you want to print 1 by 1 centimeter, you need to have a 1 by 1 membrane with nanometer scale features. So in this case, it's very easy to make the illuminating system. It's almost impossible to make the mask. So this kind of a concept that was believed to be the next generation lithography system, it doesn't work. But it still operates in some niche cases. So this is called X-ray exposure system. The very popular system, it's called electron beam lithography. It's an extremely popular system. I don't even need to show it to you. You take an electron beam, you take a electron beam sensitive photoresist, and you write, and since you can focus the electron beam to the dimension less than a nanometer, you can actually you have a very sharp pencil, and you can write features with nanometer scale. And but, this was an invited comment, but it's very slow. And you can do the calculation. Let's say you write with this pencil at a rate of like 1 gigapixel per second. You work at 1 gigahertz. So you can print 10 to the 9 pixels per second. But if you are writing with 10 nanometer, to remind you, is 10 to the minus 7. 10 to the minus 6 of a centimeter. So if you, on 1 by 1 centimeter, and you have a resolution of 10 to the minus 6, you have 10 to the 12 pixels. So if it's an electron beam, which you write 10 to the 9 pixels per second, which is very fast. 1 centimeter square will take you 1,000 seconds. So it's a very slow. But it's a very good system for research. Every university has one. And I mean, in my research, I printed nanometer lines 25 years ago because it's available. You can do it for research. This is ideal. So how to make electron beam practical for manufacturing? There is a new concept called electron projection lithography. You take electron beam, and instead of having a sharp pencil beam, you open it. You make a parallel beam, and you let the beam go through a mask. And then you can get the image of the mask. And what you do, you use some electron optics to focus the image. So instead of dealing with very high resolution mask, and as I told you for X-ray, if you want to print 10 nanometer, you need the 10 nanometer mask, which is very difficult to make. You solve one problem, you generate another problem. But if you have electron optics, I didn't tell you what is electron optics, but you can take electrons and make them move like in a lens. Instead of having in a parallel motion, they can converge. So you can take an image of your mask and make it smaller. You can project your mask using electrons instead of using photons. So this is called electron projection system. It's in the last 15 years, it's under very intensive research. This is the shape of a mask of this kind of a structure. Usually it looks like a chocolate kind of chocolate bar. Because the mask is very thin, so to make it stronger, you put bars of material to hold it. Most of the masks are made of silicon because silicon is available. So this is an opening. This is the bars. So this is the mask, and this is how there are some R&D tools which are available. This is an exposed 300 millimeter wafer. Chip size is 20 millimeter by 25 millimeter. And this is resist exposed. This is not photoresist. This is e-beam resist, electron beam photoresist. It's a polymer that is affected by the electron beam. And there are such polymers. So this is called electron projection lithography. And now we go to even more wild methods, or how to go over the Rayleigh limit. Because everything, in optical, we love optical systems because optical systems are available and we have light sources. And we have a lot of problems with X-ray and electron beam systems. So maybe the solution will come from projection electron systems, but let's look at other systems. There's one technology which is actually a pretty old one, and now people are rediscovering it. It's called near-field scanning optical lithography, or the idea is very simple. If I want to overcome diffraction, I'll put the wafer very close to my mask. Because if I put it very close to the mask, I work in the near field. In any optical system, the light is propagating. Next to the diffraction, we have something what we call near field. And we go far, then we have the far field. All the optical limits, everything that we discussed today, are far field problems. All the Fourier imaging and the Rayleigh limit, all are due to the assumption that we work in the far field. We are away from the mask. If we go very close to the mask, we can actually print very high resolution. So what you do, you build a feature which looks like you tell me how it looks like. It's an opening. You illuminate with the laser from the back side, and here you have the light is being concentrated here, and you put it in a very close proximity to the wafer. Now this device, this structure, this nozzle, you can make a device with thousands of or millions of these nozzles. And you can open and close them by using optical switching. So you can print, 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 and every time you open and close, because when this nozzle is open, and you can close and open and close it by electro-optical methods. When this is open, you print. When this is closed, you don't print. So this is it's called NSOL, this method, near-field scanning, near-field scanning optical lithography. We have few. This is the left, the tapered optical. This is the hollow cantilever. It's a cantilever structure. It's actually, if you are familiar with the tool which is called AFM, atomic force microscopy, this can be on a beam of a AFM cantilever. A typical feature today, this is people found out that they can get a very nice. The hole not necessarily has to be square. This is called a bow tie hole. So if you take a hole which looks like this, you can actually, this is a simulation of the field. This is the hole, and the red is the spot of the light on the wafer. So people found out that the most efficient image is if we take a bow tie, this kind of two trapezoid structures, and the light becomes concentrated here due to some optical effects. And we can get a very, very sharp point of light, and this can be in the nano scale, in the nanometer scale imaging. And you can, instead of one hole, you can make an array of holes. And this is the machine. This is published very recently. They make like an array of holes, illuminate it, and they can print and print and print. And every time they open and close the shape that they want to, the shape they want to print. It's like needles, but instead of the mechanical needle, it's like a light. And only the ones which are open are printed. And you can print in very high resolution. This is near-field optical scanning lithography. And you make the mask by a certain process. I will skip this mask because we are going to review mask making when we talk about processing. The second new concept, which actually we have such a tool in our university, and my students are using it, and it's pretty old concept. It's called nano printing. Imagine you take a stamp. You know what's a stamp? You put it in ink, and you can stamp, you can print the ink. So if you manage to have a stamp with dimension in the nanometer scale, you can print nanostructures. So we transfer the problem from making the process, how to make the mask, how to make this. So you have to spend a lot of money or efforts to make a very high resolution mask. And then you can print it. And what you do, you dip it in a polymer or dip it in your target, and you can print it directly. Now, this is maybe not so good for electronic circuits, because the problem here, as expected, you have a lot of defects. Any particles, some problem. But it's very good if you want to print nanostructures of chemistry, to print drugs or to print biologic material, to print proteins, to print DNA. So this technology is very useful for nanotechnology, because you can print materials directly on your target. So you don't need the whole process of putting photoresist and etching and et cetera, et cetera. You directly print your target using, it's stamping, it's practically stamping. So, and you can actually do, for example, you put your material, and another way to do it, you put the polymer, you put your stamp, you press the stamp, you lower the stamp into a material, for example, illuminate with ultraviolet to stabilize the photoresist, remove your stamp, and then you get the structure on the bottom. It's the same like, in the kindergarten, people play with plastilina, with polymer. You take the polymer, you put your finger into it, you take the finger out, you have the shape of your finger inside the polymer. So this is stamping. It sounds stupid, but it works. It works for many applications, not so much for electronics, but very useful for MEMS and for biosensor applications, because it's a very cost-effective method. It's called nano-imprint lithography. This same picture here, it's a much better shape. You put the polymer, you put the mold, you push the mold, you take it out, and you have the shape of the mold. This is it. Advantage of this technology, you can do it on flexible substrates, not necessarily on silicon. You can put the photoresist, press it, release, and you have the photoresist on the flexible substrate. And you can even think about it, you can do it reel to reel. This is called reel to reel. You put, instead of printing of wafers, you can print on sheets of plastic or sheets of paper. So you take a roll, this is your, you put your like ink or your polymer here, you put your polymer on the reel goes up, you put the template. This is like the same way people use today to print newspapers. How do you print a newspaper? You put the paper, you took the master, you put ink, you push, you throw away the paper. So why not do it for microchips? So this method of print or nano-imprint lithography system on printing on very big substrate, is attracting a lot of attention, especially for biochip and flexible electronics. So this is one thing. Another issue is called soft lithography. Soft lithography is a similar, this slide maybe should be before. Another name to call it is soft lithography. It's a liquid precursor, for example. We put some liquid precursor on top of it. The liquid is cured, and then we put the stamp, remove the stamp, and we have the structure. But, okay, so this slide should be before. I will not go into details, but I will go to details to the next one. You can actually use chemistry to help you to do printing. For example, let's say you have a very sharp pen. And this sharp pen, I magnify it, and this sharp pen is so sharp, so this is the molecules on top of it, they go down. And when they go down, the molecules they like each other, but you know, they want each other to be in a certain distance. So you put a molecule, the molecule becomes fit in the structure according to the other molecules. This is called assembly. So what you do, you have some kind of a seed structure, and the molecules are going down the tip, and as they go down, they assemble themselves to fit this lattice structure. So this is called deep pen lithography or scanning probe lithography, or you can actually take your tip and write, like this is NANC, whoever published this, I should have mentioned it. You can write their name or on the structure with drops, and the drops can be as sharp as the size of the tip. And if you can take a nanostructure tip, and this specific one, the molecules here are with thiol. Thiol is a sulfur hydrogen molecules. And if the substrate is gold, surface of gold attracts very much thiolated molecules. And the molecules, like soldiers, are being organized one by one. And you can print. This is called deep pen lithography. Professor Chad Mirkin was the first person to publish it. You have a tip, the molecules are going down to the structure, and they are become organized. This process is called self-assembly. It's like crystallization, but it's not a crystallization. The molecules like to be in a certain order. So this way we can actually print structures using deep pen lithography. The last crazy lithography, if it's called directed self-assembly, the last 10 minutes are like a collection of future things. None of this is useful or commercialized or maybe something I don't know, but it's a kind of for you to show you there are new directions, or so there are other things than the optical lithography. Directed self-assembly is an interesting concept based on what's called block copolymers. So under certain, if you take these specific polymers, they tend to assemble in this beautiful collection of lines that looks like an abstract picture, but it's not so useful. But under certain conditions, they can be assembled in this structure. So this is called directed self-assembly. If you give them some initial conditions by some treatment of the surface, they will assemble to have this beautiful arrangement of lines that might be useful to some application. So this is called a PSA, directed self-assembly. This specific one, they use 193 nanometer lithography resist. So they use a conventional high-resolution optical lithography to generate this line. They use this is the structures, and if they put the polymer on top of it, they can generate between these two lines. The molecules will get ordered in this much higher resolution structure. So this concept of directed microlithography, this is like something that is under investigation, because you can print lines, and between the lines you can print much finer lines by just you put a polymer, and it will arrange itself to give you the desired pattern. And they actually generated this beautiful periodic structure by printing these lines using optical lithography, as I showed you before, and the molecules assembled themselves. The assembly was done by directed self-assembly. So in summary of the lecture, and today was, I have to tell you, this was a really quick review on lithography. I rounded some corners, and I did not explain a lot of things. I kept it open. And definitely, if you want to know more about lithography, you have to take more serious class just on lithography, because today I covered a lot of topics, and some of the slides I did not explain all the way to the end. But if we summarize, today you can print down to about 10 nanometer, actually near 7 nanometer, with a very high throughput. This is optical lithography. E-beam lithography is very high resolution and slow. There are many emerging new nanolithography methods, deep pen, and solid nano imprinting. Soft lithography for nanobioprinting is very important. And the last slide, this is just for fun. We didn't talk about the economy, but I just found this interesting slide I want to show you. This is the price of the lithography tool as a function of the year. And this is in a log scale here, in a semi-log scale. So when I graduated, the price of a tool was in the $1 million range. This was a mercury lamp eye-line steppers. And when XML lasers were introduced, every point here is a price of a commercial tool, without names. So if you put the price of commercial tool, and this is 2005, here we crossed the $10 million, and this is going up. And when we go to 2010, the forecast actually was pretty accurate. We are now about here. So if you're talking about, you see that if we continue this line, about 10 years from now, the cost of one tool will be, I don't want to extrapolate. It will be uneconomical to use it, because there's some, you cannot pay a certain amount for exposure tool, because when you buy, every time you buy system, you want it to be cheaper and better. You're not going to pay $10,000 for a cell phone. So one of the biggest limits for resolution and for system and for performance today is not the law of physics. It's not due to the law of physics or to the law of other things. It's because of economics. The cost of the lithography tools became too expensive. It's another kind of food for thoughts when you go home to think that life is not only engineering, there's some economics involved also. And if you find a more economical way to use tools that we have now, it has a very important value. So this is the end of lithography. Next week, Yakov will give the lecture. I'm not sure either him. Okay, we have to find out who's giving the lecture next week. It's either me or Yakov. And we'll follow the schedule. We'll put all the lectures in the website. Thank you. We finished in time, so I'll see you next week.